The battery's dead, and now we'll never find Leo the lion. Grrr!
I can't believe my mind. Steve, you can't give up so quickly. We have to make our own battery.
Well, what ho, Caligny? Lucky for us, there's a chem lab right here.
Grrr! Who has entered my den of electrochemistry?
Who is that? And can we help us?
Hi, my name is Leo the Lion, spelled L-E-O, and I go grrr, spelled G-E-R. I bet you all know what that means. Well, L-E-O means lose electron oxidation, and G-E-R means gain electron reduction. Remember that, kids? Let's make a battery!
But jeepers, Caligny, look at here. It looks like the Sarari stockroom has already provided us with zinc sulfate, copper sulfate, aluminum sulfate, and magnesium sulfate. And they're metal electrodes too.
Let's check that the voltmeter works.
That's right. The voltage should read 0 when the probe leads are touched together. Let's prepare our cell by putting 25 drops of sulfate solution into each of these spot plate holes with their corresponding electrodes.
Remember though, in order to keep the battery running, make sure to add a salt ridge. The salt ridge is a strip of filter paper placed in KCl solution.
But why do we need this? Well, Caligny, you see, in order to keep the system running, we need a constant source of negative ions to balance the positive charge accumulating on the oxidizing side of the reaction.
And now we have a battery! Wait, you have to determine the voltage by touching the lead to the electrodes. Holy mackerel, they look like alligators. They have teeth, but they're just alligator clips. If you do it right, you should have a positive voltage. If you're wrong, then switch it. And now we have a battery! Wow!
Hey kids, by the way, here's a great way to remember which one is the anode and which one is the cathode. When the potential voltage reads positive, then the red side is the cathode, and the black side is the anode. You can remember this because Kathy, as in cathode, was in the red cross, as in the red side of the cross, which is positive. And now let's see if we can make the battery work and attach it to our car.
I don't think that worked. The battery is too strong. It'll blow us up. How can we make a weaker one? I have some magic solution. 6 molar ammonia is the stuff of the gods.
But Jeebus, that's a beautiful idea. Why, if we add ammonia, an oxidizing agent, to the copper side of the copper zinc cell, it'll bind to the copper 2 ions to form a complex ion that's really hard to reduce, and that reduces the voltage.
Wait, put those gloves on and make sure you add it 1 drop at a time and stir, stir, stir with a toothpick. Is it working? Observe the color change. If it did, copper 2 ion is present. And lo, the voltage has changed. We'll do it again because I have another magic solution up my sleeve. You can test this later with my magic 2 molar sodium sulfide. Just do the same thing with a new cell. Let's try out our new battery. to save us. We can make a homemade battery with the convenient supply of 2 strips of lead, a 9-volt battery, a 6-molar solution of sulfuric acid, a beaker, and some alligator clips.
Yes, you know what? That's right. Yes. Using these lead strips as electrodes, you stick them in the beaker like so.
Oh wait!
Be sure to sand the strips to remove any excess oxide and transfer the strips out to the air. Right, Lion? Thank you for the great advice. As I was saying, use these lead strips as electrodes. Then add 30 milliliters of the 6-molar sulfuric acid. Then take the alligator clip like a battery, pass it into the lead strip like to initiate the flow of electrons from the 9-volt battery into your cell, and voila! It has power!
And now we can wait for a minute for it to charge.
What is happening at this point?
Well, my friend, this is what you would call a redox reaction. The lead strip at this electrode is being oxidized from lead to lead 4+. And then water is being reduced to oxygen gas, and then it reacts to lead 4+ to form lead oxide. And now, let's test if our actual battery works. After charging for about a minute, we can connect the voltmeter to the 2 electrodes to see if the battery actually works.
Are you pointing to it or?
And yes, look, it does work. We have potential. Now that our battery is fully charged, we can go ahead and attach our LED light.
But there are 3 LEDs. Which one should we use?
We can use whatever color we like. If you attach it to the electrodes right here, it'll turn on.
Oh my gosh, that is so cool. It's green.
I know.
Wait. Why are there different colors in the first place?
Oh, well, they're different colors because as the electrons travel from the anode to the cathode, they release a certain amount of energy. This energy goes into the LED material and excites this electron. The band gap is the distance between the electron's normal state and their excited state. The larger the band gap, the more energy required to jump that gap. Purple lights have the highest energy, and red lights have the lowest.
Wow, that is so cool. Wait, this was called the discharging process, right?
Yes.
Wait, so what was happening at this point?
Well, in the discharging process, at first in the charging process, the lead electrode was the cathode because it was being reduced. And the lead oxide electrode was the anode because it was being oxidized. However, in the discharging process, the electrons travel the opposite way, making this the anode, and the lead oxide electrode the cathode. They have switched places.
Oh, that makes sense. So the lead here loses electrons and is oxidized and turns into lead 2+, which reacts with the sulfate ions in solution to form lead sulfate. And the electrons that are busted out over here go onto this side and bind and are taken into lead 4+ and the lead oxide to form lead 2+, which also interacts with the sulfate ions in the solution here to form the same lead sulfate.
Wow, I feel incredibly enlightened. Thank you so much. Now we can finally go on our journey to find the legendary Vesper Viper, the valence shell electron pair repulsion Viper.
Yay!